Independent and dependent events, part 3. All right, example 4, using a two-way table to determine independence. A satellite TV provider surveys customers in 3 cities. The survey asks whether they would recommend the TV provider to a friend. The results given as a joint relative frequencies are shown in the two-way table. Determine whether recommending the provider to a friend and living in Long Beach are independent. All right, so determine whether recommending the provider to a friend and living in Long Beach are independent. Remember, we looked at joint relative frequencies in the last section, and recommending to a provider, so that means our response is going to be a yes, and living in Long Beach. All right, so we're given a two-way table, which is nice, and here is a reminder of what we need for this problem. So we've got conditional probability and independent events. All right, so these are our conditional probability have-to-haves. And then conditional probability formula is here. We learned this in the last unit. All right, so let's say recommending the provider to a friend. That's a yes response. That's going to be our probability of event A. And then our event B would be living in Long Beach. So let's use this statement right here. So we want the probability of B given A. And we want to know if that equals the probability of B. All right, so the probability of A, let's do probability of A is yeses, and the probability of B is Long Beach. All right, so that just kind of keeps this straight on what we're thinking about as probability A and B. And the only reason I chose that is just the order it's written in. Recommending the provider to a friend, that's our yeses. That means if you recommend it, or if you did not recommend it, it would be a responsive no. And living in Long Beach rather than these other two places. All right, so we're going to do probability of B given A. So that means for this problem, let's look at the probability of B is Long Beach. So we're going to have Long Beach. And that's given, we recommended them, which means the response is a yes. All right, if you remember, in order to do this, we have to do the yeses and Long Beach over all the yes responses. Okay, so this is from the previous section, but this is the formula you use for conditional probability. All right, so the probability of A and B, so yeses and Long Beach, yeses and Long Beach, that's 0.32. So that's going to be 0.32. So again, the probability of A and B, again, a yes response and living in Long Beach. And that's going to be over all the yes responses. So all of these responded yes. So we're going to have to add up these numbers. All right, so we've got 0.29 plus 0.27 plus 0.32. And that's going to give us 0.88. And again, we don't really like to have decimals and fractions together. So if you want to just move the decimal over 2 places, that's the same as 32 over 88. But what we need to do is just find out what that is. So let's do 32 divided by 88. And that's going to give us about 36.4%. We can round that to about 0.36 or about 36%. All right, so that's the probability that Long Beach given a yes response. All right, so again, that is my probability of B of A, and now we need to know, does that equal the probability of B? Probability of B is the ones that live in Long Beach, so that's 0.32 plus 0.04. If we add that up, that is about 0.36. What do you know? That's about 36%. So, because the probability of the ones that live in Long Beach is approximately equal to the probability of Long Beach given a yes response, that means these two events are independent. So, yes, independent. Example 5, finding the probability of independent events. A spinner is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. All right, so we want to get a 5 on your first spin and a number greater than 3 on your second spin. So let's say let event A be 5 on your first spin. So event A is going to be 5 on first spin. Okay, an event B is going to be a number greater than 3. So that's going to be a number greater than 3 on second spin. All right, so that's just kind of reminding us what event A and event B are, and that just helps when you come back to the probability of independent events. We know we're going to multiply these two if they're independent, and that's how we can get started. All right, so if we spin a spinner and it stops on any one of these numbers, it says it's divided into equal parts. Okay, so what is the probability that it will stop on a 3? All right, so probability that it stops on, or not a 3, sorry, stops on a 5. We're looking for a 5. All right, so the probability that it stops on a 5. So there's 8 equal sections. So the probability it stops on a 5 would be 1 out of 8. All right, and the probability that it stops, I don't know why I put a B there. Let's see. The probability of greater than 3, that's where I keep getting the 3, greater than 3 is, all right, now these have to be independent events because what you spin the first time is not going to affect where it lands the second time. So you spin it again, and what is the probability that it lands on a number greater than 3? So 1, 2, 3, 4, 5. So it's going to be 5 out of 8. And because these are two independent events, we know that we can get P of A and B. P of a 5 and greater than 3 is going to equal the probability of 5 times the probability of greater than 3. All right, so the probability of rolling as 5 or spinning a 5 on the first time was 1 over 8. And the probability of greater than 3 is 5 over 8. And if we multiply those together, let's do okay, so 1 divided by 8, and let's multiply that by 5 divided by 8. And that's going to give us about 0.078. 0.078. So that is about 7.8%. So the probability that you get a 5 on your first spin and a number greater than 3 on your second spin is about 7.8%. Example 6, finding the probability of dependent events. A bag contains 20 $1 bills and 5 $10 bills. That means there's 25 total bills in here, right? You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. All right, because you set that aside, that means the second time you draw, there's one less than the previous time. That's going to make this one a dependent event. All right, so find the probability that both events A and B will occur. Event A, the first bill, is $10. Event B, the second bill, is $10. All right, so remember 20 $1 bills and 5 $10 bills are in this bag. Okay, so the first time you draw, all right, and it already tells us what events are what. So it says event A, the first bill is 10. Event B, the second bill is 10. Find the probability that both events A and B occur. All right, so the events are dependent, again, like I said, because there's one less bill in the bag than the second draw than there was on the first draw. All right, so the first thing we need to do is find the probability of A, right here, probability of A. So what is the probability of event A? The first bill is a $10 bill. All right, so let's say probability of A, or drawing a $10 bill, is what? So there are 5 $10 bills in the bag. So there are 5 chances to draw a $10 bill, and there's 20 plus 5, so 25 total bills in the bag. So you can reduce that to 1/5. All right, now we need to find the probability of B given A. So the probability, I keep doing that. I don't know why. All right, I keep writing down a B because I'm thinking probability, but then I'm thinking about event B. So the probability of B given A. Guess I'm just getting ahead of myself. All right, so event B again is the second bill is a $10 bill. Okay. All right, so if you've already drawn one $10 bill, that means there's not 5, now there's only 4. All right, so there's going to be 4 $10 bills possible to draw. That's what makes this dependent, because there's one less. And now there's only 24 bills in the bag instead of 25. And again, you can reduce that. 4 goes into 24 6 times. All right, now what we need to do is say this right here. We're going to do the probability of A times the probability of B given A. So we're going to have 1/5 times 1/6. So that's going to be about, or it's going to be 1/30, because 5 times 6 is 30. And that's going to be about what? So 1 divided by 30, 0.033. So that's going to be about 3.3%. So the probability that you draw 2 $10 bills, you draw a $10 bill the first time and a $10 bill the second time. So the probability that you draw 2 $10 bills out of a bag with 20 ones and 5 10s is about 3.3%. All right, this was a long lesson, but we are finished. If you have any questions, please let me know.